again.
Okay, thank you.
Yeah. Yeah, so if you have 0, so I just made that 0, okay?
Yeah.
But in that case, I just took the difference between those two. So that's the change in temperature. And here, I took the difference as well. But then I did not take the difference between those two because I think, when you added 60 mil,
yeah, that's it.
It's got to be definitely more than 19.1.
Yeah.
But that's way too small difference, right?
Yeah.
There are two things going on. So if you add more, so one thing you have to understand is that, let me just write it here. So regarding adding, so there are two players. There are two players when it comes to change in temperature, okay?
Which is the change in enthalpy?
No. I'm not talking about enthalpy at the moment. So I'm just
Okay.
talking about just change in temperature, okay?
Okay.
So if you mix more acid and base, then more heat is generated, right?
Yeah.
This would cause the this is likely to cause temperature to rise higher. True.
Yeah.
So for e.g., if you add a 50 ml of NaOH base and 10 ml of acid, that's going to produce less heat than 50 ml of the base plus 20 ml of the acid. True.
Yeah.
That's what I'm trying to say.
Yeah.
Second player is that the volume of water. Okay. The volume of water. If you have more volume of water, it takes more energy to heat, to change the temperature. Okay.
Yeah.
So even though, in terms of the Q, this will generate more heat, right?
Yeah.
But then this is 70 mil, whereas this is 60 mil.
Yeah.
Okay. So it depends on the temperature. So let's say so let's say you have a 50 mil of base and then 50 mil of acid, and then versus a 50 mil of base and then 60 mil of acid. So we talked about how they're equal in terms of energy generation, right?
Yeah.
Because it's, there's only 50 mil of base to react with.
Yeah.
So even if you add 60 mil,
Matter.
well, there's 100 mil here and then there's 110 mil here. So which one is going to rise temperature more?
The second one.
The first one.
Oh.
The first one, yeah. So the amount of heat generated here and here, they're the same. However, there's less volume to heat up, all right?
Yeah.
Therefore, think about it.
Less energy to do it. So
it requires less energy to raise the temperature. Yeah. Right? So there are two players when it comes to changing temperature. The more volume you have, the less the temperature, okay? So if I just summarize this, the more moles react, the more temperature change, okay? Yeah. The higher the temperature. The more the volume, the lower the temperature. You see, there are two players in this. So when you add, just take a look at this. When you have 20 mil, 50 mil, that generates less energy than 40, 50 mil, right?
Wait, which one? The 2050.
So if you have 20, 50 mil, yeah, that'll generate less heat than 40 reacting with 50, true? Yeah. So this generates more heat and this generates less heat, right? Mm-hmm. However, there is more volume to heat up, right?
Yeah.
So the fact that so the idea that I'm trying to convey to you is this is a battle between the moles reacting versus the volume. The volume. So if you want to generate more heat, then you got to increase the number of moles as well as the volume. Is that right?
Yeah.
So if you increase the number of moles, then you're generating more heat, right?
Yeah.
But at the same time, if you are trying to increase the number of moles reacting,
You have to increase the volume.
you have to increase the volume. But what does this try to do? This will try to increase the temperature, but this will try to drag the temperature down.
Yeah.
However, you can see that the temperature is still increasing, right? Even though, so see, this will generate, so I'm just gonna copy and paste that over here. But the idea that, so you have to really try to understand me here.
Yeah.
When you look at that versus that, okay, this will generate this much heat, whereas this one will generate this much heat, right?
Yeah.
But then there is less volume here, there's more volume here.
Yeah.
So if we don't know this result, then we cannot really figure out whether this is going to rise to a higher temperature. Like it could have been going like this, 19 degrees Celsius and 20 degrees Celsius and 19 degrees Celsius.
Yeah.
But there's always this battle between the volume. There's more volume, so temperature would be lower, but then there are more moles reacting. So it's battle between those two. So you can see that the clear winner is this guy, right?
Yeah.
This is the winner.
Yeah.
Because you can see that the temperature is still increasing even though there is large volume. See?
Yeah. So then is that why I mean, obviously the 19 is a very big outlier compared to like,
yeah, so just ignore that.
But when I'm talking about like the results, like when I'm analyzing them.
Yeah, so here, what I did was, so that guy is really difficult to understand because, you might say that's an outlier.
Yeah.
But if you understand this, what I explained over here,
yeah,
you've added so this does not generate any more heat than 50-50 when this is 50-50. But at the same time, you have, so there is
a lot of volume.
So you might think that that's going to be the winner. And when that takes over, then the temperature doesn't rise as much. So if you truly understand that, then you could be a little bit cautious about ruling that out.
Yeah. Yeah, no, because I have to analyze and kind of talk about why. But yeah,
but when I thought about it more carefully, I think that is a clear outlier.
Yeah.
All right. Yeah.
Because I mean, the volume is big, but it wouldn't affect it by that much.
Yeah. So so the volume is, so if it was 50-50 rather.
Yeah.
50-50 rather, then I think it'll still be an increasing trend because, as you can see, it is an increasing trend, isn't it?
Yeah.
But I think that is definitely, it has gone down way too much, even below that.
Yeah, exactly.
So that's why I didn't take any value for this.
Yeah.
I just didn't count the difference between those two. I just ignored that one. In the second experiment, I ignored that bit there. That was just way too high.
Yeah.
If you look at it, it's just way too high. See? So that is also an outlier. So I didn't take the difference between those two.
Yeah.
Now in the third, I think everything was fine. So between that and that, just
Yeah.
consider it as a 0 degree Celsius change. And that's a 3 degree Celsius change, and that's pretty consistent with that one and that one.
Yeah.
And this is pretty reasonable, and I think that's also reasonable as well. You can see that you see how these two agree with each other? So that's how we know that that's an outlier there.
Yeah, exactly.
Right? So I'm only taking these values, this one and this one and this one, and I take the average of them. Okay, so this is the average of that is just 0. So I just reproduce the table again, and these values are the averages. So that's average of 3.4 and 3.8 and 3.
Yeah.
So that's average of those. Yeah.
With the last table, you know how it goes from, like, there's a slight decrease in the last one and the 5 value is quite high compared to the 3 value? Is that like a big deal, or?
Yeah, I think you still have to use that data though.
Yeah, but as in, like, when I'm like talking about it and like analyzing it, in terms of like, would that be like maybe an external sort of heat source?
So I think that is completely understandable. Whatever the initial temperature that was measured, that is the initial temperature. So we can't really change that.
Yeah.
And I think it is expected that this goes down a little bit. It is actually possible. The reason is there is just way too much volume.
Yeah, okay.
So the temperature increase could actually be, in fact, less than this one.
Yeah.
Okay. So that's 5.7. It's a very good point you made. So that's 5.7 there, 5.8 there. So they pretty much agree, right?
Yeah.
But then there's a 6 there, and there's a 5.7. So if I can just explain this again, it's very, very important. When you have 4 of those, and then 5 of those, 5 of the base, and then 1, 2, 3, 4. So that's with the 40 mil versus 50 mil. Okay.
Yeah.
Then you are generating. This is going to generate. So that will react with that, and that'll react with that, and that'll react with that, and that'll react with that, and will produce
only 4.
like 1, 2, 3, 4 energies, right?
Yeah.
But then this energy will be used to heat up 90 mil. Yeah. Whereas when you add, I'm just going to draw this again here, and then you have instead of 5, you went 6, right?
Yeah.
And then this will produce only 5 of those, right?
Yeah.
So you're not creating much higher heat compared to this one. So it's only 4. This is only 5, right? Even though you have 110 mil, you only have that much energy to heat it up, right?
Yeah.
So the temperature of this one, the temperature change of this one was like 5.8. It is completely understandable that the actual temperature change for this one is only 5.7.
Yeah.
That makes complete sense.
Yeah, because it's not that much more. Yeah, no, I get
that. Because it is making it, so 110 mil is making it much more difficult to raise the temperature.
Yeah.
So it makes it difficult to raise temperature. Okay.
Yeah.
At the same time, this is not too different.
With the experiment, so obviously the
from that one.
experiment.
So this, in fact, could actually be lower. Yeah.
Yeah.
So with this one here, you take the average, and all I did was plot that, and then this graph here is simply the plot of change in temperature, which is those values there, versus the volume added.
Yeah, okay.
So when you don't add anything, then there's no change in temperature. When you add 20 mil, then you have about 3.4 degrees Celsius change. when you add 40 mil, then about 5.75. And then when you add 60 mil, because we're taking average, it's just slightly higher, you know?
Yeah.
So the energy generated is equal to just MC delta T. So it's equal to 50 gram times by 4.18 times by the change in temperature, that's 0. That's equal to 70 grams. 70 gram goes through 3.4 degrees Celsius change. Here, 90 grams goes through 5.75 degrees Celsius.
The averages, are you?
So we're using the average temperature change.
Yeah. Okay.
So we're just using this equation, MC delta T, using the average temperature change. Then you get this. So if you plot those two, then you get this one. But if you plot the energy produced versus the number of moles of HCl, that's given by the concentration times by the volume. Because number of moles, number of moles is equal to CV.
Yeah.
So it's 1 mole per liter. That was the concentration times by volume. So if you add 20 mil, then you times it by 0.02. So I'm just going to actually write this as 0.02 because it's 20 mil. And this is 0.04. Now, I got to be careful with this one. It's not going to be 0.06 because when you add 60 mil, it is still just going to be the 50 mil of the acid that matters, right?
Yeah.
Not the entire 60 mil. So this is actually going to be 0.05 of the acid and 0.05 of the base. So you do that. And this is the graph generated when you plot that versus that, the number of moles versus the amount of heat generated. And as expected, it's a straight line because the amount of heat generated is proportional to the amount of number of moles that has reacted, right?
Yeah.
And this graph, the gradient will give you the delta H. So let me just explain to you why.
Is that the same as doing it as the formula, like the Q equals?
Yeah. So if you look at this one here, so we know that delta H is equal to Q over N. If we just ignore the negative sign, we just want to know the what is it, the positive value, let's say. We can just ignore the negative sign, okay?
Yeah.
Then you can see that the Q equals to delta H times by N, true? So this is like Y equals to MX. So if you have this side is the X, so this side is the N, and this side is the Q, and that's exactly what we have here, number of moles here, and amount of the Q, right, the heat, true?
Yeah.
Then you can see it's a straight line with there's no y-intercept, right? So it's 0.
Yeah.
That's why it's 0 there. And you can see that the gradient must be the delta H. So that's why the gradient, because that's M, So gradient is equal to delta H. All right?
Okay.
And in this case, the delta H is equal to 54,305 joules per mole. And that is pretty similar to, this is 54.3 kilojoules per mole. And of course, the delta H, it's a negative value, so you can just take a negative value for that. And that is very similar to the published value of 57.9, I think. So if you look at the HCl.
So that's for the overall experiment.
That's not for, I wouldn't say for the overall experiment. It is the result that we get from all of the results.
Yeah.
Yeah. Yeah. And we're just trying to generate a single value from all of these results. So what we did was trial 1, 2, 3, and we took the average and we plotted graph from it.
Yeah.
And the gradient gives you the result that is from all of these trials.
Okay. And you said it's close to the value that's
it's
like
very close to the true value between. So if I just type HCl NaOH, the heat of neutralization, it might be in your crack report as well. So that's actually 55.2, isn't it?
When you say the heat of neutralization, is that the amount it takes to neutralize the like reaction, or like what do you mean by that?
Sorry?
Like when you say the amount of heat to neutralize it, or whatever you said, what do you mean by that?
So all we're trying to do is figure out the delta H, right?
Yeah.
So sometimes, so you're wondering about the terminology called the heat of neutralization, true?
Yeah, like because that's the name of the experiment, but we're measuring enthalpy, so like I don't get. Yeah.
Okay, sure. That's a very good question. So when it comes to, by the way, you can see that the answer is a 55.2, right?
Yeah.
I'm not really sure what they say that one. I'm just gonna come back to this later. Oh, that's HCN, so just don't worry about that. So we're just concerned about that one. And that is the same value pretty much. So we calculated that from this gradient. So this is what needs to be in the report. Okay, so all of this table, this graph, it needs to go into your report. Okay.
Yeah.
And you have to say that this is pretty close to that one there.
Yeah.
That is the published value, and this is the result that we get from the 3 trials, the school experiment that your teacher conducted, and they agree. That's what you need to say. Okay.
Yeah.
Now, so let me just talk about that heat of neutralization thing. So when we talk about the delta H, this is known as change in enthalpy. And the unit for that is kilojoules, or sometimes just kilojoules, or sometimes kilojoules per mole, right?
Yeah.
So what that means is how much energy is absorbed if it's endothermic or released when 1 mole, so when we're using that one, okay, 1 mole of some substance is consumed.
Yeah.
Okay, so for example, when we have the HCl, NaOH, and it gives you the NaCl with H2O, then it gives you delta H equals to negative 55 kilojoules per mole. And we can say it is per mole, but when you say it's per mole, people might wonder, per mole of what?
Yeah.
So in this case, they say of water. Or you can say, because it's all 1-to-1-to-1-to-1 reaction, you can say it is of HCl, or you can say of NaOH, of Na, of water, whatever,
Yeah.
doesn't matter. So what that means is that when 1 mole of this, 1 mole of this react to give 1 mole of that, 1 mole of that, then 55 kilojoules of heat is liberated. Understand?
Yeah.
So what would be if you have 2 HCl reacting with 2 NaOH, giving you 2 NaCl and 2 H2O, then what would you say to be the delta H?
Of either one of them. So you
So
do
if you
work
have
out
1111, then you have 55 kilojoules per mole, right?
Yeah, so you just double it.
So, however, when you double it and then still say per mole, then it would be wrong, because when you have 1 mole of HCl, you get 55 joules. When you have 1 mole of NaOH, you get 55 joules, right?
So when it's 2 moles.
So you can see that when you use the word per mole of any of those, you see,
Yeah.
that it must be negative 55, true?
Yeah.
So when you are still using this term per mole of, let's say, any of those, then it still must stay 55 kilojoules, regardless of these coefficients, right?
Yeah.
Yeah, because when you say
That
per mole, you have to
law.
refer to this one. So
Is that
if you,
Hess's law?
yeah, not really Hess's law, sorry.
Okay.
So if it's 2, 2, 2, 2, you have a choice. You either go with this one, or you can say simply just negative 110 kilojoules and don't bother with the per mole.
Yeah, okay.
What that means is when 2 mole react to give 2 mole, it will give off negative 110 kilojoules, and we don't care what the mole is. But as soon as you use the word per mole, it has to refer to one of them, okay?
Okay.
So you have 2 choices. That's why I'm saying that if you have the delta H, can be written this way or this way. All right?
So is the just saying it that that's the enthalpy of neutralization, is that just telling you that
Yeah,
water
we'll now move on to enthalpy of neutralization.
Yeah.
So when it comes to, the word enthalpy of neutralization, we also call it heat of neutralization. You can have a heat of neutralization, enthalpy of neutralization, or like combustion. You have all sorts of things: combustion, atomization, solution, heat of solution. Or you can also say things like, what is
And they're
it?
all the same.
No, they're not all the same. They're all different kinds of reactions.
Oh, right.
Heat of combustion, atomization, solution. You can also have heat of formation. You know how there are like many different types of reactions out there in chemistry? And neutralization is simply just one of them. It's just reaction between, acid and base.
So when you say heat of neutralization, that's the same as enthalpy of neutralization.
Yeah. So we use these terms interchangeably when we are referring to delta H.
Yeah.
Okay. So when you say, heat alone is just a Q, right? But when you say heat of neutralization or heat of combustion or heat of atomization, then we have these terms: delta H neut, delta H at atom, delta H formation, delta H of solution, heat of solution, delta H of combustion. Okay.
Yeah.
So we simply add those little subscripts to indicate. So if you can see HCl with NaOH, you can say delta H for that equals negative 55 kilojoules. So you can say that the enthalpy, change in enthalpy, is negative 55 kilojoules per mole, or you can say delta H neut equals negative 55 kilojoules per mole.
So it's just the type of the experiment, of the reaction.
Yeah, it's just indicating what type of experiment it is.
Yeah.
So let me tell you about the advantage of doing this stuff, okay?
Yeah.
So when you have So for example, formation O2, H2, add to give H2O.
Yeah.
And then you can say, you can put half there and then that's balanced, right? Or you can double it to give O2, 2H2, giving you 2 water. So
Yeah.
there are two ways of writing the equation.
Yeah.
Let's suppose that the delta H for that is 1 kilojoule per mole. So I just don't know what the figure is, so I'm just going to make it 1, okay?
Yeah.
Now, so there are a lot of ways of doing this. So of course, let's say just delta H, and I'm not going to use the word per mole here, okay?
Yeah.
Then what you need to write for this one is how much? It must be 2 kilojoules, right?
Mm-hmm.
So if you don't use the word per mole, it just means it's the energy that is released as per equation.
Yeah. Literally
Half mole of that, 1 mole of that, and 1 mole of that, then it's 1 kilojoules. It's just double. So like you said, it's Hess's law. It's simply double version of that. So you got to double that, okay?
Yeah.
But if you're using delta H equals to 1 kilojoule per mole, then what you need to do is you have to say of something, right?
Yeah.
So you can see that it'll be of what? It has to be either H2 or H2O. It cannot be the O2 because you can see that this is not 1 mole here. That's 1 mole, that's 1 mole, right?
Yeah.
So you got to write, if you want to use the word per mole, then you got to do that, okay?
Yeah.
Now here as well, if you have a delta H and you have two choices. So it's 1 kilojoule per, you can still do that, 1 kilojoule per, okay, so if you're doing 1 kilojoule per mole, so even with that equation, you can have 1 kilojoule per mole as long as you write of H2, so this might be a bit confusing, or H2O, okay?
Yeah.
But you can, for that equation, you can say it's, but you can see that this is 1 mole here and 2 mole, right? So it's convenient to say 2 kilojoules per mole of O2, understand?
Yeah.
And there's another way of doing this, which is, you see how this is really annoying?
Yeah.
So we write delta H of formation, we can do formation. So when it's referring, when you have formation, that means it's per 1 mole of whatever is being formed. You can see that this equation is a formation equation, right? That and that is being formed into that one. So when you write per mole, kilojoule per mole, this per mole here is always referring to the substance that is being formed. So you can see when 1 mole of water is being formed, it's 1 kilojoule, true? So you can write 1 kilojoule. And even if you have that equation with 2 mole there, you can still write 1 kilojoule per mole. Doesn't matter what the equation is.
Okay.
So you still write 1 kilojoule because when you have 1 mole of that, you have 1 kilojoule, right?
Yeah.
Yeah. So you still write that. That's the convenience of using these little subscripts. So what we're trying to do, coming back to this one here, when it comes to heat of neutralization, so we're calculating the delta H, right?
Yeah.
But we are also referring it to as heat of neutralization.
Yeah.
Because they're the same thing. And because everything is 1 mole in this equation, as soon as you find a delta H, that's the same as the heat of neutralization.
Okay.
So yeah, it's a bit confusing at first. It's like one of the most confusing areas in introduction chemistry. Okay.
Yeah.
Yeah. So we'll call it a day here. I'll wait for you. I'll wait for your report. Once you finish your report, just send it to me and I'll have a look and give you some feedback, okay?
Okay, thank you. Also, just quickly,
Yep.
With the report, do you reckon like bond enthalpy and like Hess's law and stuff is relevant or not?
For the report, I don't think so.
Yeah, I didn't think so. Okay. No worries. Thank you.
So I hope it wasn't too confusing. Yeah, we went through a lot of stuff today, like this stuff here.
No,
You
it
know.
makes sense.
Yeah. Okay.
Thank you.
Cool.
Okay.